Okay, so in experiment 8, we focus on diodes. So we'll talk about why do we use them, various applications for diodes, and we'll mainly focus on these four types of diodes. So the small signal diode, which has a part number of 1N4148, it is the common diode that we are going to use to allow current to only pass in one direction. So that's the part number for that, 1N4148. Then we have the Zener diode that is mainly used for voltage regulation. The part number for that is 1N751. We are also going to use this. This is going to be part D of experiment 8. And then we of course have the light emitting diode and the photodiode. These are both in relationship with light. So one produces light, LED, and one senses light, the photodiode. Um, and of course the LED comes in a variety of colors. Uh, so we are going to be talking about this general set of diodes in this experiment. So let's see. We'll start with what the symbol for diodes is, what is its purpose, and the general purpose, and then we will go into specific applications. You have seen diodes perhaps in experiment 2 or probably in experiment 3. So way early in the semester, you have seen such a symbol, which is for the diode. And it has two terminals, and we are going to call them the positive terminal and the negative terminal. Specifically, those are anode and cathode terminals. We are denoting the current that passes through the diode as I sub D and voltage across that diode as V sub D. And the triangle and this straight line denote the direction of current. So as you can see, the triangle points to the right, which is the same direction in which you have the current flowing. Now, how are we achieving this current only in one direction? Well, the way the diode is constructed is by using two doped semiconductors. One is of p type and one is of n type. All that means is this is the p type is excess holes, and the n type semiconductor has excess electrons or excess negative charge. And in the middle over there is an intrinsic layer. We call that the depletion layer. So what is going to happen when we connect, for example, this particular diode to a voltage supply? In this case, I'm using a DC voltage supply just for the sake of discussion. So the positive terminal, as you can see, is connected to the p-type material, and the negative terminal is connected to the n-type material. Of course, what is going to happen in this case is the positive charge is going to repel this positive charge, which makes it move closer to the depletion layer there. And the same thing will happen over here. The negative terminal, negative charge gets pushed closer to the depletion layer there, which will make the depletion layer go away or become very, very small, which results in direction of flow of current to be from P to N, or from the anode to the cathode. That happens only when we are connecting a positive terminal to the p-type and negative terminal to the n-type. In other words, when I connect a higher voltage on the anode compared to the cathode. So that's when the current is going to flow. And as you might imagine, if I reverse this uh, polarity of the voltage source, in that case, the charges are going to move the other direction. So they are going to move this way, away from the depletion layer, thereby increasing the depletion layer, and now the charge cannot go from P to N. So now we will not be able to get the direction of flow. We will not be able to get the flow of current in that case. So when we have a positive terminal connected to the p-type material, we call that region forward biased. So forward biased is the exact same figure that is shown over here, positive connected to positive. And when we reverse either the diode or the supply, then we go into a reverse bias situation. So at this point, I hope you guys can guess what is going to happen. Forward bias, you have current flow. Reverse bias, you do not have current flow. And when you go into well, we'll talk more about the details about the biasing regions in a little bit. But that's sort of the symbol followed by the general purpose. So the general purpose, I can say, is to allow current to pass only in one direction. Um, so some of the applications, there are many applications for a diode. Some of the applications that we are going to discuss over here include fast switching. So if you want a device that can switch from the forward biased to a reverse biased region, meaning there is flow of current and there is no flow of current, very, very quickly, we can use the diode to do that. The 1N4148 diode will be able to achieve fast switching up to a rate of 100 megahertz. That is based off of its data sheet. So that's pretty fast switching. Um, what else? So we have rectification, voltage rectifiers. So what does that mean, rectification? It simply means I can convert an AC current to a DC current. So something that changes with respect to time to something that is constant with respect to time. So a rectifier. That's another application for a diode. There is voltage limiter. So if I want to clip a voltage signal and make sure that it is always between plus and minus 1, for example, I can use a limiter to do this. Uh, there is obviously the light applications. So the LED and photodiode allow us to do light applications, light sensing. Um, Generation and sensing. Uh, what else? Let's see. Voltage regulation. Another very important application of a diode is voltage regulation, and this is specifically for the Zener diode. What that means is I need to regulate the voltage, which means that I do not want the voltage between 2 points to change much. I want it to be pretty much the same, irrespective of how much current flows through it. So even if I change the current a little bit between those 2 points, I should be able to maintain the voltage regulation. And I can do that using a Zener diode. And we'll talk about that as well. So these are some of the applications. In Experiment 8, we'll be exploring most of these applications. So let's see. Let's move and talk about the most important aspect of any electrical component, which is the current voltage characteristic. So just to remind ourselves about what we have been dealing with throughout the semester, we'll start with the IV characteristics of a resistor. So just for a resistor, how is the current through the resistor related to the voltage across the resistor? So to do this IV characteristic, we are going to consider a circuit over here in which we have a AC voltage source, and we are calling that V in. We have connected that to a resistor R, and we have grounded it on the other end. As simple as that. And we are calling the voltage across the resistor to be VR, and the current in the circuit, which is also the current in the resistor, to be I sub R. And my goal is going to be this, to sketch the IV characteristics of this resistor. So for that, I will start off with establishing a x-axis and a y-axis. On x-axis, I'm going to try to sketch voltage across the resistor, VR, and on y-axis, I can say IR, so current through the resistor on the y-axis, and this of course is 0 right in the middle. So as you might imagine, because we just have a resistor R, Ohm's law is going to be the relationship that we need to consider. And Ohm's law says voltage across the resistor is directly proportional to the current through the resistor multiply, so, and the proportionality constant is the value of the resistor itself. So V equals IR. And if I use this relationship and I apply that to this graph, what I'm going to end up with is a straight line. And that particular straight line will, of course, pass through 0. And we can also figure out what the slope of this line is going to be. The slope of this line, because we know the relationship is V equals IR, and we are plotting VR on the X, IR on the Y, which means the slope of this line should be 1 over R, the value of the resistor itself. Okay, so that's your voltage current or current voltage characteristics of a resistor, a linear relationship based off of Ohm's law. And we can also get a glimpse of what is the IV characteristic of the capacitor and the inductor, which we have studied earlier in the semester. So for a capacitor, we said the C dVc divided by dt. That is going to be I sub C. So the current through the capacitor is the value of the capacitor multiplied by the time derivative of voltage across it. And similarly for the inductor, we said V sub L is L di L by dt. Voltage across the inductor is equal to the value of the inductor multiplied by the time derivative of the current through it. So a linear relationship for the resistor and a differential relationship for a differential and integral relationship for the capacitor and inductor for current versus voltage. However, now let's try to look at what it is going to be for the diode. So we will try to do it theoretically, so using a mathematical equation. We will try to do it experimentally, and we'll also try to do some processing with that experimental data. So let's try to do that. So over here we focus on IV characteristic of the diode, and it's the same diode 1N. Let me just write it down over here. The diode we are considering here is 1N4148, and it appears in this schematic over here. Again, a AC voltage source connected to a resistor R1, which is connected to a diode. Let's call it D1. And on the right, I have the current voltage characteristic that is given in the experiment 8 write-up. I essentially just picked up the figure from there and I pasted it over here to see how the circuit diagram relates to the figure A-3 in the experiment write-up. The first thing that I would like to discuss is the different regions in which the diode can operate. For example, if I move all the way to the right over here, if I'm going to look at this region over here, that is called the forward biased region of the diode. Okay, so let's see. I'm going to be focusing on this region here, forward biased region. And what are the some of the things that I'm going to worry about in this? Well, what is the voltage across the diode here? It is small, but in the positive direction. So 0.1, 2, 3, 4, and at some point the current through the diode rises exponentially, very dramatically, right? But beyond a certain voltage across the diode, we are not able to explore that region. So no matter how much you increase the voltage across that diode, the current is increasing. However, the voltage is not able to increase across that diode. And that particular value around which this typically happens for the 1N4148 is 0.7 volts. So around that 0.7 volts value for the 1N4148 as well as the Zener diode 1N751, in the forward biased region, the current is going to increase exponentially beyond that value. So imagine a valve that you are opening and closing. So ideally, if you are below 0.7, the the valve is closed, meaning there is no current, a very small amount, but theoretically it is zero, below 0.7. So the diode requires a turn on voltage, a minimum voltage of say 0.7, a threshold voltage, to turn on, so the valve opens and then the current can flow in that particular direction. And depending on what we have connected to that diode, we will know how much current will flow through it. And we'll talk more about that in just a bit. But that's as far as the forward biased region is concerned. Notice over here, the voltage across the diode can never be 1.2 volts or 1.5 volts across one diode, as we are seeing over here. It is going to be between 0 to 0.7. Maybe experimentally we may be able to get about 0.75, for example, just a little bit more, but not too far ahead. So just keep that in mind, so that when we get to the experiments, we can relate this to the IV characteristics. Next region that we are going to talk about is the reverse biased region. So the reverse biased region, as you can see, the voltage across the diode is negative. So essentially that means that over here we have connected, say, -1. Over here we have connected a bigger voltage, right? So this voltage is lower than that voltage, and that when that happens, the differential voltage across that diode is negative in that case. um, and when it is negative, a very very small amount of current called the saturation current, I sub s, flows through the diode, and it is negative direction, so it's a negative current. And the typical value for is is of the order of nanoamps, so very 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 small. That's what happens in the reverse bias region. And as you keep increasing that value all the way back to a certain voltage, say for example -100 volts for the 1N4148 diode, it is going to break down at that voltage. That means that we have applied so much negative voltage that the depletion region between that P and N type material goes into the breakdown region, which means after this point all the charge or all the current will start flowing through the diode, but it is going to be negative because now it's going to be in the negative direction, the other direction. So it's not going to be from here to here, it's going to be from in the other direction. So that's your third region, the reverse breakdown region. So three regions: forward bias, which is the good region there. Reverse bias is essentially valve is off, and reverse breakdown region is when you have turned the knob too far back, in the off region. Um, so that's your IV characteristic of the diode, and uh, if if we can get some experimental data over here, to see if it is correct or not, we can actually fit a mathematical equation to this IV characteristic. So exactly the same way we have done that for resistor, capacitor, and inductor, it turns out we can get an exponential function to fit the I versus V for the diode. But that's going to be only for the forward biased region, because we are never going to be able to go to -100 volts using the analog discovery. So we'll have to settle for -5, or we can get to -10 by using the negative power supply as an offset. So we'll take a look at that as well in the experiment. So 3 regions, we talked about the terminology a little bit. Now let's go on and take a look at the circuit. So if we have this particular circuit here, my goal is going to be to see what happens to the diode. So as you have this voltage source and it is going up and down, right? As it goes up and down in the positive and negative direction, the diode is going in the forward, reverse direction at the same frequency, because now this guy is going up and down, positive, negative, and so on. And when it is in the forward biased region, so let me just quickly sketch over here. Uh, well, let's actually do this. Let's actually figure out um, what this is going to be. So what I'll do is I will, for example, take that, and this is going to be my time. This is going to be my voltage. So if that's my voltage waveform, then my forward biased region, let me color code it here. Let's see, if I pick blue for that guy, forward biased, all of this is going to be the forward biased region, because I'm applying positive voltages over there. And then my reverse biased region is going to be over here. That's when the diode is going to be in the reverse biased region. So when it is in the reverse biased region, no current flows through the diode, which means no current flows through the resistor, which means the voltage across this resistor is going to be 0 at that time. So all the input voltage is going to appear across that diode. All of this is going to appear across that diode there in that case. Let's see. So diode, okay, that's what we are trying to explore the IV characteristics. So that's why it is present in the circuit. But why do we have this R1 in the circuit? Well, the answer to that is the I, right? You see, we need the current information. ID. How are we going to find out ID experimentally? So the way we do that is by using two voltage channels. One channel 1 is going across the diode, so we get the voltage across the diode using that. So that's essentially going to give us the x-axis information, right? So that's this guy right there. And the y-axis information, which is the current through the diode, for that we are going to play a little trick here. What we are going to do is we are going to take our second scope channel, 2 plus and 2 minus, or blue and blue stripe, place it across the resistor R1 with a known resistance value. We are going to measure the voltage across the resistor R1, right? So that's measure, say VR1, and then if we divide that measurement by the value of R1, we are going to get IR1, which happens to be the same as ID because they are in series. So essentially we are using this R1 as a current sensing resistor. It is allowing us to sense how much current flows through the diode, because we need to know, as we are changing the voltage, where do we stop? Do we stop here, 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 here? Where do we stop on the y-axis? Well, that is going to be dictated by the voltage source and the resistance that is connected in series with the diode. Okay, and that's how we do that measurement, and we'll take a look at more details when we do the actual measurement uh, today. Let's take a minute here and take questions. Uh, Anode and cathode are names for positive and negative terminals. It is not just for the diode, it is for the positive and negative terminals for anything, a battery, even for a battery, you can call that anode and cathode. Those are names chosen for positive and negative terminals. That's a generic term. For LEDs, it is used for. Uh, you will see that in many places. Other questions? So in our case, we are going to have to identify which one is the positive or the anode and which one is the negative or the cathode, because before putting the diode into our circuit, we better know what is the direction of allowed current. What is the allowed direction of current? So if we want it to flow in one direction, then we are going to have to orient our diode appropriately and then put it in our circuit. um, you know you might remember when we were doing this experiment, in which you remember when we were doing the uh, LC circuit. We were doing the inductor capacitor resonance. We used a diode so that the energy exchange is only between the L and the C. That's when we use this diode. Um, so the question is, the conventional current flows from positive to negative. Yes, but the electrons actually move from in the absolutely right. Yes. So that's a very good point, Corey. So anode and cathode, this is the direction of current id, which is the direction of conventional current, which means the direction of flow of holes or positive charge. It is exactly the opposite of flow of electrons are moving exactly in the opposite direction. So that's essentially the difference between your physics classes and your electric circuits classes. uh, so in physics, you might be talking about electrons moving from one point to the other, in which you consider cathode to anode. And in all of your circuits, we have been talking about current, which is essentially the movement of positive charge from positive to negative. No problem. Okay, so we talked about some of the details in this. Let's get to some problems over here, and I'm hoping that with certain questions in certain circuits, we will be able to learn a few more details about the diode. And again, we still have one N4148 diode. We have a voltage source, and now we are specifying what voltage source that is. So it's a amplitude 5 sine 2 pi 1 kt. So the frequency is 1 kilohertz, which right away tells me that the time period for this source TS is going to be what, 1 millisecond. The amplitude is 5, and my goal over here is to sketch V out, which is the voltage measured across the diode, and we will also try to find out peak ID, and ID is the current through the diode. Because we have a sinusoidal or AC voltage source which keeps changing, we are going to have a current also which keeps changing. We are only interested in finding the peak, the highest current that can flow through the diode, as long as the voltage source is 5 sine 2 pi 1 kt. And while we are doing this, we'll try to sketch Vs, V out, and in fact, if we know Vs and V out, voltage across the resistor should just be the difference between the two. So we'll actually sketch all three. Um, we'll start with Vs, which is given, so that should be straightforward. Let's say I have, uh, let's see, I'm going to start with an x and a y axis here. And let's zoom in there. Let's call the x axis time. Let's call the y axis voltage. My units are volts here. My units are seconds over here. let's sketch the source voltage, sure, in black. Sure. Assume that this is right. I know it's not absolutely right, because that guy went up till there and that guy is shut it up. But assume that this is 5 sine 2 pi 1 kt. I hope you can bear with me a little bit. Let's see a few things that I can mark very quickly. If that is 0 on the time axis, this is going to be 1 millisecond, because the time period is 1 millisecond, and this is also going to be 0.5 millisecond there. Sure, okay, so we have a one period and sum that we are sketching for, and let me also label here that is Vs as a function of time, Vs of t. Next, I'm going to try to sketch voltage across the diode, for example. And what we learned about voltage across the diode is, as we increase Vs from 0 to 0.1 to 0.2, all that voltage will be across the diode, because during that time ID is 0, which means VR is 0. So all of that voltage should appear across the diode. However, if we keep increasing it, it cannot go beyond 0.7. 0.7 is when it taps out. So let's say I have a marker for 0.7. So for example, if I say, all right, say this is 0.7. And this is of course not to scale, but I'm just going to assume that it is. This is -5 there. So until 0.7, it is going to keep rising. So I'm going to sketch the voltage across the diode in, let's pick green for that. So I'm going to have all of that region, follow the source. At 0.7, it will not go beyond that, so it'll flatten out there, and then as it comes down, it will follow the source. Now what is going to happen when it goes negative? We already talked about this. When the voltages are negative, we are in the reverse bias region. Reverse bias region, no current through the diode, or a very very small amount of current, which is negligible. So theoretically zero current through the diode, which means zero current through the resistor, which means zero voltage across the resistor. So all of the input voltages are going to appear across the diode here. So again, it's going to follow the same pattern as the source. Let's see if I can trace over my own sine curve. And over here again, it'll follow there, and then it'll flatten out at 0.7. So the green guy is what? It is voltage across the diode, and we are actually calling that V out in our case as a function of time. So that's that guy right there. So we got source voltage, we got the output voltage or the diode voltage. What are we left with? We are just left with the voltage across the resistor, and this is going to be very simple. Why? Because voltage at the source is going to be split up between the resistor and the diode, or in this case, let me just write V out here, because VD is V out. And if I want to sketch VR, it is simply going to be Vs minus V out. And I know Vs and V out over here in black and green. So I'll just find the difference between the two and sketch it as VR. So between 0 and 0.7 volts, they are going to be 0. Let's see here, 0 until that time. And let's do the simple thing first. Whenever it's equal, so from here to about here, again it is 0. In the middle, it'll change. So let me sketch in the middle. So what is going to do is, when I find the difference between Vs and 0.7 here, it is going to increase sinusoidally and then it is going to decrease over here, and it's going to do the same over in this case over here. So beyond that it will simply increase there, and that difference is going to be 0.7 volts. So clearly, what is that value? Let me use blue here. That value should be 5 minus 0.7, so 4.3 volts. So I can say the peak voltage across the resistor, is 4.3 volts. So that's VR max is 4.3 volts, which implies that IR max is going to be 4.3 divided by, what do we have for the value of the resistor? 1K, which is equal to 4.3 milliamps, and this is also the peak ID, because IR max is the same as ID max. So that's your peak ID. All right. So I hope this example was useful. A few key things that I would like to for you to take away from this: the sinusoidal voltage is going up and down, so that's the full cycle. That's your Vs. However, if I were to look at only the resistor voltage across the resistor, you are only getting positive half cycles. So it's like we have eliminated the negative half cycle. If we measure the voltage across the resistor, only the positive half cycles are uh, being preserved. There is a difference. We are subtracting 0.7. However, we are only able to get the positive half cycles of the sinusoid across the resistor. This is going to be useful when we start talking about the rectifiers. Okay, questions about this example? Okay, let's move ahead a bit. Let's talk about this example over here. Well, I've actually done it. So let me do it again. So what I have over here is a voltage limiter, and there's a reason why we call this the voltage limiter. So let me work on this again with you. I have a few more diodes in this case. So I have a voltage source, I have the same resistor, doesn't matter what the value of the resistor is. I am just going to be interested in sketching voltage across the source versus voltage across the output, which over here, V out is being measured at 2 points where there are two paths. There are three diodes over here, there are two diodes over here. So how is this going to work? How am I going to sketch Vs and, more importantly, V out? So for Vs, the story is pretty much the same. We start with the sinusoid, and we sketch it, and again the points are going to be very similar. That's going to be 5, this guy is going to be -5, and what else, this is going to be 1 millisecond, and this is going to be half millisecond, so that's fine. Now what is going to happen as you start increasing this voltage on the positive side? So during the time where we are in the positive half cycle, or here and here, well, as you are increasing Vs in the positive direction, these two diodes are in the reverse biased region. However, these three will be in the forward biased region, which means that they will be able to function as three valves that are connected back to back. And I would need 2.1 volts to turn on three back to back diodes that are connected in the same direction. And over here I would need negative 1.4 volts to turn on the negative side, because when you have negative voltages over here connected to the negative, so it's like being forward biased. It is forward biased. So on the positive side we are going to get a limitation of 2.1. So let's me draw two lines over here. One is 2.1 roughly over there, and the other is 1.4 roughly over there. And using the blue marker I can sketch the voltage across the output, which is going to be the voltage across those two parallel paths. So on the positive direction is going to limit to 2.1. On the negative, actually let me take a different color here. So on the positive is going to go to that point, limit at 2.1, come down as the source, and then limit at negative 1.4, and then of course do that. So essentially, and that is my V out. So I can say this guy is 2.1 volts and this is negative 1.4 volts. So essentially what I did was a voltage limiter application of diodes. And in one example, we have seen how we can get different limiting voltages on either side of the diode. Okay, so I think this is good for the voltage limiter. We will start talking about the half wave rectifier in just a bit. So if I go to my experiment 8 write up, if you just give me a minute here, I'm going to scroll through and go and look at the half wave rectifier and get rid of a bunch of stuff here. And similarly over there and there and there. Okay, so let's talk about rectification. Again, the rectification amplification, rectification application of the diode um, occurs in two forms. The half wave rectifier that we see in figure B-1 of your experiment write-up. So that's your half wave rectifier. I was hoping a little bit better there. Okay. Sure. And the other one is the full wave rectifier. So let's try to see what happens in the half wave rectifier. In the half wave rectifier, we essentially chop off all the negative half sinusoid and preserve the positive half cycles of the sinusoid. So for example, if I were to use wave gen to generate a sinusoidal voltage, and I'm still using a diode and resistor in series, and I'm right now measuring channel 1 is measuring the wave gen and channel 2 is measuring the voltage across R2. And in our earlier discussion we saw that if we configure our circuit with two elements, resistor and diode, and if we were able to measure the voltage across the resistor, it is going to essentially be eliminating the negative half cycles. It is just going to preserve the positive half cycles of the wave gen source. So if your wave gen is doing this, your voltage across the resistor R2 is essentially going to be doing this. And we saw that. So by using this half wave rectifier, what I'm able to achieve is input is this and the output is this. And somehow, if I was able to smooth this out, I can get a rectified output. And I smooth it out by applying or connecting a capacitor between the two in parallel to the R2. So if I connect a smoothing capacitor in parallel to R2, what is going to happen is I'm essentially going to be charging the capacitor up until this point, and then I'm going to discharge slowly, charge it back up again, discharge slowly, and so on. So what that gives me is a wave that looks like this. So as you can see, we started with complete AC, we went to sort of positive half sinusoids, and then we went to a little bit of a DC voltage, right? So we went this application of a rectifier is exactly to do that. It is to go from something that changes with time to ideally constant with time. So we are able to get that a little bit using the half wave rectifier. Um, Now, one key thing that I would like to point out over here is if this is my source time period, let's call that TS. It is the exact time period between my ripple. So all of this is called ripple. So you see this is a ripple. So the change in voltage, that is my ripple voltage. And obviously, if I want this to look very close to a DC signal, I want as small of a ripple as possible. But that ripple voltage is going to go high and low with a period of TS, the same time period as the source. So make a note of that, because we are going to next do a full wave rectifier in which the time period will get halved, because we will use both the positive half cycles as well as the negative half cycles. Um, Question about what a half wave rectifier is, the application, how are we able to achieve this using a one diode, one resistor, and the smoothing capacitor. Now, I hope you guys will be able to say what happens if your capacitor is big and small. So let me see if I can write capacitor big here and capacitor small there. So if you have a smaller capacitor, then you are going to discharge faster, and if you have a bigger capacitor, you are going to discharge slower. So if you want to reduce your ripple voltage, then you want to use a bigger capacitor as your smoothing capacitor. Okay, so let's talk about the full wave rectifier now, which is going to be a little bit more complicated than the half wave rectifier. Earlier we just had one diode, now we have four of them, and they are connected in a particular configuration to allow the half cycles, both of the positive nature as well as the negative nature, to be available at the load. So both positive and negative will appear across this load resistor. So to do this, I would like to explain this by first going over the positive voltages. So what is going to happen when this particular voltage source over here, so the voltage source is here, and this guy is a AC voltage source. It can produce voltages that change with time, um, and of course they can be positive or negative. So what would happen when they are positive? Well, when they are positive, some diodes are going to be forward biased, some diodes are going to be reverse biased, and only the forward biased diodes, they will be current through only the forward biased diodes. So let me try to trace the direction of current when the voltage source has positive voltages that are being supplied to this full wave rectifier. So to trace the positive voltages, what does positive voltage mean? There is positive here, negative here, right? There's a, you know, 5 with respect to 0. That's 5 with respect to 0, for example. um, so how am I going to be able to trace the direction of current? So for that, I'm going to use a highlighter, and I'm going to go through this circuit highlighting the direction of flow of current. So comes out of the positive terminal there, and at this junction the diode on the right is forward biased because we are talking about the positive voltages at the source. The left one is reverse biased, so it's going to take this path, go through the load resistor, come back up here, go through this diode, and go back to the source. And let's see, so that's going to be a complete loop. Two diodes are being used here, and essentially the load, whatever voltage across the load is going to be, V load in this case is simply going to be voltage across the source minus 1.4, because we used two two forward bias diodes over there. So that's as far as the positive half cycles are concerned. What about when the AC voltage source gives us negative? Well, for that I'm simply going to erase whatever I had before, and I'm going to assume that there is a negative voltage being applied, and I'm going to again try to trace the direction of flow of current. So starts with this guy, goes up to here, and at this point it's going to go through here, come back up through the load, come back down and back in. So as you can see, it is using the other two diodes in the other direction when the negative voltages are there. But the point is, the load sees both positive and negative half cycles. So even for the negative, we have the same relationship. But now they are going to be negative. So you see this? If the input is of this form, the voltage across the load is going to be like this, because we are essentially flipping the negative cycles to the positive side by connecting it in the full wave rectifier configuration. And then if we were able to connect a capacitor across this load, so suppose we connect a capacitor between those 2 points like we did earlier, we will be able to smooth that out. And we talked about the time period between those peaks before, right? So we said, okay, the time period between this guy and this guy, if that is Ts, in our half wave rectifier, that was the same time period, uh, because we were observing those two peaks. Then the negative one was getting eliminated. Now clearly we are using both of them, so this is going to be half. So essentially it puts less uh, limitation on the size of the capacitor, which means that I will be able to get a better rectified output with the same capacitor if I do a full wave rectification as opposed to a half wave rectification, because I'm doing that discharge only for half the time, and then I'm quickly recharging it back up. So that's a quick discussion on half wave and full wave rectifier. We will be doing experiments on these two circuits on Monday. We are going to spend the remaining of the class period trying to uh, sketch the current voltage characteristics of the diode using MATLAB, Analog Discovery, and the proto board. Okay, so what I'll do is I'll stop the recording and then I'll take your questions.